Employment and job creation are often looked at as key factors in analyzing the economic strength of a nation, particularly in the US. One factor not discussed often enough is absenteeism, which can be defined in a broad sense as the habitual absence of an employee from their place of work. Absenteeism's effect on the economy has been considered prior in a number of studies. One such study by Grinza and Ricks for the IZA Institute of Labor Economics found that for a 1% increase in employee absenteeism, productivity declined 0.24% on average. A similar study in Japan found that of 6,700 employees citing neck or back pain as physical causes of absenteeism, or depression, anxiety, and emotional disorders as psychological causes of absenteeism, high wage and performance loss were observed. From an economic standpoint, the annual cost of depressive symptoms related to absenteeism in the US is approximately $44 billion, with up to 9.7 to 14 hours per week of lost productivity among chronic sufferers. The objective of this project is to use census data to determine what factors most predict absences of workers in New York State. We can then prescribe the best approaches employees can take to reduce absenteeism and the associated wage loss, in addition to how employers and public institutions can best serve the population to reduce the need for employees to be absent from work, subsequently reducing the loss in productivity. The problem statement is twofold. The primary aspect of the problem statement is what demographic, employer, and socioeconomic factors selected from those collected from individuals in New York State for the US Census result in employees being absent from work. As a secondary measure, the problem statement will also consider, can the trends in New York data be extended to other populations to create a more universal model for predicting the likelihood an employee will be absent. The primary dataset used for this project is the US Census data filtered for individuals in New York State. Some of the categorical variables selected were educational attainment and industry. Binary variables selected included sex, maternity status, health insurance coverage, and disability, and continuous numeric variables used for model building include age, number of persons in the household, number of children, and wages or salary in the last 12 months. The second data set used to address the second part of the problem statement was titled Absenteeism at Work and was composed of records over a 3-year period from a large courier company in Brazil. This dataset contained demographic and socioeconomic factors, as well as a response detailing whether or not the employee had been repeatedly absent during the time period of analysis. Feature engineering was required to filter, clean, and transform our initial set of factors. It was not uncommon for some factors to have missing values, which could be attributed to the person not reporting the status for that factor, or it not being applicable to the person. Factors with missing values accounting for a small portion of their data, about 2%, were dropped. Factors with a large percent of missing values were dropped entirely from the analysis, such as household presence and age of old children, which had 22% of values labeled as missing. In addition to handling missing values, we transformed some factors with respect to their categories and values. One such variable was education level, which included categories for every grade level and type of degree, resulting in 24 categories. To reduce the number of categories, we split this factor into 3 buckets: bachelor's degree, graduate degree, and other. A similar process was used to create categories for the factor work hours per week, since the values were heavily imbalanced as shown in the graph on the right. This bucket was split into full-time and part-time workers. We also considered transforming the response variable. The response variable was imbalanced, as in the original dataset, persons that were absent only accounted for 2% of the data. Oversampling was applied to balance the data and include more samples that are labeled as absent. One variable available in the census data is a person's weighting, which is how much does this person represent the population. Our oversampling method was to apply this weighting to people who were labeled as absent. Using a function of the weighting raised the representation of absence to approximately 10% of the data. After preprocessing and feature engineering, the correlation was measured for the selected variables. As shown in the correlation matrix, none of the predictor variables show a particularly strong correlation with the response absent at first glance. Only a few variables appear to be correlated with each other. For example, the variables number of children, NOC, and number in household, NP, are correlated with the category household presence and age of children, HUP-AOC. These variables could be combined or dropped in future analysis. Logistic regression was used with and without the weights, and the top table shows the initial results for the top 10 variables with unweighted absence. The top 3 variables are whether a person has given birth within the last 12 months, whether the person has a disability, or whether the person has insurance through their employer. The result for absence with the weights applied are shown in the bottom table. The top 10 variables with weighted absence are similar, 8 of the 10 are the same, with oversampling, and the coefficient values are greater, since the categories for absent samples have greater representation.
After our initial analysis, we continued with lasso regression. We chose the lasso model to reduce the number of final features. First, we split the data into training, validation, and test sets. We trained the lasso model using tenfold cross-validation to determine the optimal value of the lambda hyperparameter. Next, the validation set was used to determine the best threshold probability in predicting absence, which was 0.023. As shown in the confusion matrix, the overall accuracy of the lasso model is 0.78, and the absence prediction accuracy is 0.51. For the purpose of this study, a trade-off of many false positives was deemed justifiable for the ability to better predict true absence. In addition to logistic regression, we used tree-based models to predict absence. The decision tree model only consisted of a root node without any branches, suggesting that the absence variable is homogeneous and cannot be split further. To further investigate whether a tree-based approach would be viable, we also tried using a random forest model. Despite the high accuracy of 0.98, we ruled that the random forest was not a good model because it predicted all samples as non-absent and was not able to predict true absence. A support vector machine approach was also used in an attempt to predict absence. However, much like the tree-based model, the SVM model produced high accuracy but was unable to predict any incidences of absence. Adjusting the parameters of the model proved to have little effect on correctly predicting absences.
Of the models trained and validated, the cross-validated lasso logistic regression model was the best for our needs in that it was able to successfully identify instances of absence. This best performing model was then run on a test set, the results of which can be seen under the confusion matrix displayed here. The model was then retrained on all the data to identify the potential influence of the predictor variables. The raw output is exhibited in the coefficient table. A figure of those predictors with p-values less than 0.05 better displays their influence on absence. The predictor variables wage and whether the individual had given birth in the last 12 months appear to be the most influential. Increasing wage appears to bring down the probability of absence, while giving birth in the last 12 months appears to increase it. Following the same procedure used to create the cross-validated lasso logistic regression model, we attempted to create models for each of the employment industries available in the dataset. The bar graph on the left displays the area under the curve value and the model accuracy value from each model. These are taken as indicators of the model's performance. Of these industries, 5 are displayed in the figure on the right with their predictors that had p-values less than 0.05. The significant predictors for each industry are largely similar to those returned from the model run on all the industries. Specifically, wages and whether the individual had given birth in the last 12 months appear to exhibit the same influence as the industry-wide model.
With this understanding of the US Census dataset, similar models were applied to absenteeism at work dataset to see if similar predictors of absenteeism exist under different conditions. First, feature engineering was done on the dataset to simplify the presence of categorical variables. Health-related chronic illnesses such as respiratory or cardiovascular diseases, etc., were grouped as reason type 1. Pregnancy or maternity were grouped as reason type 2. Uncategorized short-term illness or other injuries were grouped as reason type 3, and scheduled absenteeism such as dental visits or other appointments were grouped as reason type 4. Since the absence in this dataset was a numerical value representing the number of days missed by an individual employee rather than a binary response, linear regression was applied instead of logistic regression for creation of absenteeism prediction model. From this model, reason type 1, reason type 3, and education level were found to be statistically significant at a 95% confidence interval. The inference from this is that employees suffering from chronic illness and injury are more likely to be absent from work, and employees with higher levels of education are less likely to remain absent. The adjusted R-square value for this model was 0.10, meaning much of the variance for an employee's absence is not explained by this model. Despite the low explained variance, there are some very important points of discussion from this model. First, the significance of reason type 1 strongly supports research articles listed in the introduction section of this report, where employee chronic illness is discussed as a strong reason for absence. The significance of education also backs up the article's claim that blue collar workers are more likely to be absent as a result of chronic illness stemming from the toll of physical labor on the body.
Tree-based and support vector machine models were not able to identify factors that could predict employee absenteeism. However, logistic regression can be used to predict employee absenteeism in New York with reasonable accuracy, with significant factors including having given birth to a child in the last 12 months, having a disability, having children under 6, and annual income. So how can we take this analysis and make recommendations to prevent productivity and economic losses? We know that lack of health insurance coverage in the US dataset and chronic illness in Brazilian datasets are factors of absenteeism, which suggests that improved access to health resources can reduce absenteeism. On-site daycare can reduce pregnancy and maternity-related absence also. Lastly, personalized support for employees with disabilities can be implemented to reduce significance of disability in predicting absenteeism. If we wanted to take this analysis further, there are a few next steps we could take. First, we could conduct an analysis over a longer period of time to assess larger samples and their trend. Next, we could compare absenteeism and its predictors over different industries and locations. In terms of the US Census data collection, we recommend redefining survey questions to more robustly capture metrics that are factors of absenteeism, and create survey responses targeted for temporary absent workers to capture conditions while they are working instead of current conditions while they are being absent. This would increase the predictive ability of the dataset.